Okay, so we left off yesterday talking about how to draw this regular old Lewis dot structures, Lewis dot diagrams for molecules. Do you remember how with the carbon dioxide molecule, I said that we could have had a triple bond on one side and a single bond on the other side? But I was like, just take my word for it, double bond is better, okay? There's a method that we can use to help us figure out which is the right drawing. Like, is the triple bond, single bond the right drawing? Or is the double bond the right drawing, okay? And this method is called formal charge or calculating formal charge. Literally, why is nothing working? There we go. All right. So, definition for formal charge. This is a calculation we can use to determine the most accurate Lewis structure. Like the one that best represents what's actually going on in the molecule itself. And we can tell that, like we can actually look at these nuclei using an electron tunneling microscope. We can actually, or electron scanning microscope. We can actually see the nuclei of atoms, which is kind of wild. Like we can see how far apart they are. And the length of the bond depends on whether it's a single or a double or a triple, right? So like single bonds are longer, double bonds are shorter, triple bonds are the shortest. So if the carbon dioxide molecule had a triple bond on one side and a single bond on the other, the triple bond would be really short. You would see the nuclei really close together, and the single bond would be long. The other side of the molecule would be more spread out, right? That's not what we see under the microscope. We actually see two short double bonds on each side. So how do we figure out that when we're drawing this Lewis dot structure? Okay, so here's how we do the calculation. And the equation isn't really going to make a lot of sense until we do an example. So underneath this calculation, or off to the side here, we're going to write the equation for it, and then we're going to calculate it, okay? So first of all, the calculation is done on each atom in the structure. So it's going to be a little calculation that we do for every atom in the structure. So like in the case of carbon dioxide, we're going to do this calculation on all three atoms. We're going to do it on the carbon and on both of the oxygens. Okay. All right. The equation is this. Formal charge is equal to the number of valence electrons that that atom has. It's your normal number of valence electrons minus the bonds and non-bonding electrons. Okay. Okay. So let's draw those two options for carbon dioxide. So remember we said that we could have done a triple bond on one side. Just do this again underneath calculation. That's why I said write small. Oops, that wouldn't have had that many lone pairs. Hang on. Sorry. One lone pair. Okay, triple bond or a single bond. This is a structure that I could have drawn when I was doing my rules for drawing, right? Where you assign all of your terminal atom electrons first, and then you make double and triple bonds as needed. Okay. All right. The other option, which is the one that we ended up going with, was a double bond on both sides. Again, I'm not doing this like from scratch, but hopefully you remember we drew this a couple times yesterday. And Brady was like, how many times are we going to draw this molecule? Okay, so now let's calculate formal charge, all right? So what you do is you look at each atom in the structure. So like I'm starting off looking at this oxygen right here, and watch my pencil marks, you guys, because that's going to help with your counting. In my head, I ask myself, how many valence electrons does oxygen have? Right, so oxygen's in group 6, so it has 6 valence electrons. All right, so in my head is 6. I'm going to subtract from that all of the things on the oxygen, all of the bonds and all of the non-bonding electrons on the oxygen. So 6 minus 1, 2, 3, 4, 5, 6, 7. See how I counted that? Okay. So 6 minus 7 is negative 1. The formal charge on the oxygen is negative 1. Okay. Carbon in the middle. How many valence electrons does carbon have? 4, right? Minus all of the stuff on the carbon, right? All of the bonds and non-bonding electrons on the carbon. 1, 2, 3, 4. 4 minus 4 is 0. Oxygen again has 6 valence electrons minus all of the stuff on the oxygen. So 6 minus 1, 2, 3, 4, 5. 6 minus 5, positive 1. Any questions on how I calculated that? Yeah. No. You start with the number of valence electrons the element has. So like if I'm doing this oxygen right here, this oxygen has 6 valence electrons. Just off the periodic table, how many valence electrons does oxygen have? And then you're going to subtract from that all of the things that we've assigned to it in the structure. So like we have assigned to it 1 bond and 1, 2, 3, 4, 5, 6 electrons. So that's a total of 7, right? How many bonds? 1 bond plus all of those electrons, 6. So 6 minus 7 is negative 1. Yep.
Why would you count bond as a 2?
Yep, because it's not total numbers of electrons, it's like things assigned to it. It's just it doesn't actually mean anything, this calculation. It's just a method that works to help us determine the right structure. Okay. Okay, let's calculate formal charges on this other option that we have, right? So oxygen has 6 valence electrons minus all of the stuff on the oxygen. So 6 minus 1, 2, 3, 4, 5, 6. Nothing. Okay, carbon, 4 valence electrons minus 1, 2, 3, 4. 4 minus 4 is 0. This oxygen, 6 minus 1, 2, 3, 4, 5, 6. So 0, right? So now we ask ourselves, like, okay, so which one of these structures is the better structure? And again, by better, we mean more representative of like what's actually going on, okay? This one is the better structure, and here's why. All right, so here's where you kind of have to write small and maybe squish in some rules here on the left side or the right side of this. Here are the rules. Fewer atoms with formal charge is better. Okay. So do you see how in the diagram with the double bonds, there's no formal charge on any of the atoms? That means it's a better representative structure of the actual thing. Over here, I've got formal charge, and I don't want it, right? So less formal charge is better, okay? Sometimes you have to have formal charge. Like sometimes your structure is going to result in one or more of the atoms having formal charge. And that's okay as long as the magnitude is not 2 or greater, okay? So if you get formal charge of plus or minus 2 or more, that is not okay. Not okay. All right? So you'll automatically know that that is not your structure if you get that big of a formal charge. All right? And lastly, if you have to have some formal charge, which again, in some cases we will, especially in polyatomic ions, if you have to have formal charge, you want the negative formal charge on the more electronegative atom, which is of course usually one of your terminal atoms, okay? So if you have negative formal charge, that's okay. Hopefully it's on one of your terminal atoms. So those are your rules. So if ever you land yourself in a situation where you're like, wait a second, I could put my double bond here, or I could put my double bond here. Or if you're in a situation where like maybe it's a triple bond and a single bond, or maybe it's a double bond situation, calculate the formal charges for both options and then pick the one with the better formal charge, okay? And I will, like on any assessment, I'll give you a hint. I'll be like, hey, draw both options and calculate formal charge, all right? When you take AP, you just have to always know to sort of be calculating these things in your head and picking the best structure. But for your purposes right now, I'll tell you if there's something funky going on, okay? All right, let's move on. Underneath resonance structures, okay, there's a definition that we need to do, but before we do the definition, I want to do an example. So we're going to draw an example of a structure, but you're going to need to draw 3 different things, okay? So make sure you start all the way off to the left, all right? Here we go. So underneath resonance, let's draw the Lewis dot structure for nitrate. All right, so we're not going to define this just yet. Let's draw the Lewis dot diagram for NO3, 1 minus. All right, follow your rules. Step number 1 is counting up your total number of valence electrons, right? So nitrogen has 5, oxygen has 6, times 3. What do I do with this 1 minus? Add 1 in. Hang on. Hello? Hi. That's okay. Yes. No, she dropped that off. Okay. You're welcome. Bye. Where did Kylie go? She go to the bathroom? When did she leave? I didn't even notice. Oh, well, they were looking for her. Anyway. Okay. Where were we? She was here. She gave me that. She gave me a bag of treats. Yeah.
Like 5 minutes ago.
Oh, okay.
You, on the equation you wrote right there, the +1 at the end is the charges.
Yes. All right. So 6 times 3 is 18, 19, 24. 24 electrons. Okay. Divide by 2 to get pairs. 12 pairs of electrons. All right. So, nitrogen is going to go in the middle, right? Because it's the least electronegative and it comes first in the formula. Can you see past me? Yeah. Okay. All right. So nitrogen goes in the middle. We're going to connect to 3 oxygens. 1, 2, 3. 1, 2, 3. Okay. So of my 12 pairs, I now have 9 pairs remaining. Okay. So those 9 remaining pairs go on your terminal atoms first. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm all out of pairs. Okay. Once you're all out of pairs, that's when you check to see that everybody's satisfied, right? Who's not satisfied? Nitrogen. So I need 1 double bond somewhere. Could be on the left, could be on the bottom, could be on the right. Pick a place. I'm going to put mine on the left. So I'm going to take away a lone pair and instead draw it as a shared pair, double bond. Now everybody's satisfied, right? I'm going to put it in brackets. And I'm going to pop my 1 minus charge behind it. Because that's what we do for polyatomic ions. Okay? Now, I told you to put your double bond wherever you want because it's going to turn out that it doesn't matter. Let's calculate formal charge. Now, maybe, hopefully some of you drew the double bond in different places, but let's calculate formal charge. Let's start with the single bonded oxygens, okay? So in my head, 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. They thought you were supposed to be taking the physics test and they called and I was like,
No, I told them I wasn't.
Yeah, I know. Okay, fine. All right, so 6 minus 7 is -1. This oxygen looks just like that, right? So again, 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. All right, let's do the double bonded oxygen now. 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6, 0. Let's do the nitrogen in the middle. 5 minus 1, 2, 3, 4. 5 minus 4, +1. Okay. Now, that's like a lot of atoms with formal charge, you know, but it's a polyatomic ion, and polyatomic ions, because they have charge, will often have formal charge that adds up to that charge. So you can see this adds up to a 1- overall. It's not a problem because there's no magnitude of 2 or greater, right? That's the only time where we'd be like, oh, this structure's garbage, okay? And the negative formal charge is on the terminal atoms, which makes sense. So like this structure is fine. Did anybody put their double bond somewhere else? Or did you guys all follow me? Yeah, you got the same formal charge, right? So if you have multiple options where the double bond can be in multiple different places and you have the same equivalent structure, like you have the same formal charge, you have to draw all of the options, okay? And I'm gonna explain why. I know you're gonna be mad. You're like, why do I have to draw all 3? You have to draw all 3 for a very reasonable reason, but let's draw them first, okay? So you draw arrows in between, and then you draw the other options, okay? So you're gonna draw your double bond in all 3 places. So this time I did it to my bottom oxygen. You okay? And we're gonna put brackets with charge. And now I'm gonna put it on my right-hand side oxygen. And brackets with charge. Okay. As you guys, oh my gosh, those are some messed up looking electrons. All right. As you guys finish up drawing those, I'm going to explain why we have to draw this all 3 times. Okay. It turns out that when we look at this molecule under a microscope, there is not 1 short double bond and 2 long single bonds. That's not what we see. We see 3 identical bonds that are about like a bond and a third. Like they're shorter than a single bond, but not as short as a double bond. And they're all the exact same length, which makes us think, it turns out this double bond is not in one place, it's in all 3 places. It is spread out over all 3 locations, right? So 1 bond divided by 3 locations gives you like a bond and a third. So not a single, not a double, a bond and a third. So we represent that. So like, obviously these electrons are moving, okay? So they're moving all the time. So the electrons that are in that double bond are spending equal amounts of time between all 3 oxygens, as opposed to just being statically in one place. So how do we represent something that's dynamic and moving with something that's a static drawing? We have to draw all 3 options. Okay, so that's why we do all 3. And that is called resonance, okay? So this is when multiple Lewis structures are needed to represent a double or triple bond that exists in multiple locations. Maybe I should say that exists like spread out over multiple locations. Okay. We actually call this, just like the electrons in the electron C model, we say that this bond is delocalized. Okay, this bond actually does in fact exist in multiple different locations. And that's why we draw all three options. Okay, so if you have a situation where you have a choice of where to put the double bond or where to put the triple bond, and it does not affect your formal charge, you have resonance. Yeah, Marie. Yeah, of course. Questions on that, on the calculation or? So even if there was no charge on this, you guys, even if this was not a polyatomic ion with the 1 minus, we would put brackets around it and draw arrows going in between each. Like that's how we show the resonance, okay? All right. Let's go on to our exceptions. We're gonna do 2 exceptions. So we're gonna do one on the left and we're gonna do one on the right. Yes, Aiden.
How do you know that or how do you know the Lewis like structure has like resonance?
So, you know, when we got to that point where like we needed to make a double bond, like we had assigned out all of the electrons and nitrogen wasn't satisfied. At that point, when you realize, wait, I have a choice between putting it here, here, or here, that's when you know there's resonance. Like when it appears that there's multiple different locations that are not going to change the overall outlook of the molecule or the formal charge of the molecule, that's how you'll know. Okay. All right. So, you know, I spent all this time telling you that everybody wants 8 valence electrons, and sure enough, there are some exceptions to every rule that we make in science, right? Nothing is super straightforward. Exceptions. I've been spelling stuff wrong all day today. All right. Let's draw the Lewis dot diagram for, this is the one to the left, BH3. BH3. So we're going to follow our rules. We're going to find out how many valence electrons boron has. It has 3. It's in group 3. Hydrogen has 1 times 3. That's 6. Divided by 2. Working with 3 pairs of electrons. All right. Boron's going to go in the middle. And we're going to connect to the 3 hydrogens. Hydrogen, hydrogen, hydrogen. All out of pairs. Okay? Is boron satisfied? No. So you're like, uh-oh. But I don't have any more pairs, and there's no lone pairs to turn into double bonds, right? But yet this is a molecule. Like this molecule actually does form in nature. And when it has less than an octet, we call it a sub-octet, less than. And some of your lighter molecules, some of your lighter atoms, like the elements in group 1, period 1 and period 2, those elements can form sub-octets. The heavier elements typically do not. But boron is up there in the second period, second energy level. It will, in fact, form a sub-octet. And the other way that we can check to see, like, hey, is this okay, is let's calculate formal charge. Okay, so how many valence electrons does hydrogen have normally? 1, minus the 1 thing stuck on it. So 1 minus 1 is 0. Okay, so all of these hydrogens have no formal charge. Boron has 3 valence electrons, and oh look, in this diagram, we have assigned it 3 bonds, so 3 minus 3, 0. Oh look, beautiful, right? So that's like a way to confirm that this suboctet is like an okay thing to have happen. If we can have less than an octet, guess what else we can have? More than, yes, the others are fine. F, 6. Let's draw the Lewis structure. All right, so sulfur has 6 valence electrons. Fluorine has 7 times 6. 7 times 6, 42. I don't even remember my multiplication tables. 42 plus 6 is 48. Divide by 2. 24 pairs of electrons. All right, that's a buttload of electrons. All right, we're gonna put sulfur in the middle. Now, carbons, you guys, will form big long chains. Molecules like this do not form big long chains, okay? It's sulfur in the middle and 6 fluorines connected to it, okay? So how do you draw that? I like to go 1, 2, 3, kind of off at an angle. 1, 2, 3, like that. All right, so 6 fluorines. So of my 24 pairs, I'm down to 18 pairs. And oh, look, I have 6 terminal atoms that each need 3 electrons apiece, right? So 6 times 3 is going to be those 18 pairs. So fill in those fluorines with their 3 lone pairs apiece. Okay? This is called an expanded octet. Now for fluorine, right? Look at the fluorines, 2, 4, 6, 8. The fluorines have 8, right? The fluorines are not expanded. The element that is expanded is the sulfur. But let's calculate formal charge and like see if this is okay, right? So let's start with the sulfur. Sulfur has 6 valence electrons normally, minus the 1, 2, 3, 4, 5, 6 things we bonded to it. 6 minus 6 is 0. So the sulfur has no formal charge. Let's calculate the formal charge on one of the fluorines. They're all the same, right? But one of them, 7 valence electrons, minus 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. So no formal, you're not gonna have any formal charge anywhere. So this is okay as well, right? But there is a rule, okay, for expanded octets. And the rule is the central atom must be in the 3rd period of the periodic table or beyond. Like it needs to be in the 3rd, the 4th, the 5th, the 6th, or the 7th period. In other words, it needs to be a bigger atom. Any guesses? Think electrons here, you guys, right? Because this is bonding. They're bonding with their valence electrons. Why would the central atom, in order to be able to expand its octet and take in more electrons, why would it need to be an element that's in the 3rd energy level or higher? What starts to exist in the 3rd energy level?
I'm forgetting the word, the name of it, but like the shell gets bigger.
Yeah, we get a d orbital that we didn't have before, right? Where does the first d appear? It's the 3d, right? There's no 2d. And I get it, the d block is below the 3rd period, but remember the d block starts at the 3rd principal energy level. So even though sulfur doesn't have any electrons in its 3d, it has an empty 3d available to drop more electrons into, okay? So in order to expand the octet, you've got to have that d orbital there for the shared electrons to exist in, okay? All right, I'm gonna stop recording. Questions, Jennifer?